It's pretty wild when you stop and think about it. Computers are just everywhere. They're in our phones, our cars, our homes. They run the entire internet. But for how much we use them, how many of us actually know how they work? I mean, really, on a deep fundamental level. Well, today, we're going to peel back the layers and look at the master plan that makes it all possible.
Seriously, just for a second, think about it. What is it that lets that little device in your pocket or the big machine on your desk actually do anything? It's not magic. It all comes down to a foundational design, a set of rules, known as its architecture.
And that's exactly what we're going to dive into. First, we'll figure out what architecture even means in this context. Then we'll look at the key parts of every computer, explore the most common design model, and see how computers actually think. We'll even touch on 2 different design philosophies and wrap it all up with why any of this really matters.
Okay, so let's tackle that first big question. What is computer architecture? The absolute best way to think about it is as a master blueprint. It's not about the physical parts you can touch, but about the grand design that dictates how everything works together. So, the formal definition says it's the conceptual design and fundamental operational structure. What that really means is it's the science, and maybe a little bit of art, of deciding how to connect all the hardware pieces to hit certain goals. Are you building a supercomputer that needs raw speed, or a smartphone that needs amazing battery life? The architecture is how you get there.
Yeah, this quote from way back in 1964 really nails it. Architecture is what the programmer sees. It's the crucial bridge between the software, the code, and the physical hardware that runs it. It defines the rules of the road for how software can talk to the machine.
All right, now that we know what the blueprint is, let's look at the main parts that the blueprint actually describes. And what's amazing is that pretty much every computer you've ever used is made from the same 3 essential building blocks. And here they are. It's a pretty simple layout, right? You've got the processor, you've got memory, and you've got your input and output devices. And see that line connecting them all? That's called a bus. Think of it like the central nervous system, or an information highway, that lets all the different parts communicate with each other. So let's quickly break these down. First, the CPU, the central processing unit. That's the brain. It's doing all the thinking and carrying out instructions. Then you have memory, which is basically the computer's short-term workspace, like RAM. It holds whatever the brain is working on right now. And finally, you have I/O, or input-output. That's how we talk to the computer with our keyboard and mouse, and how it talks back to us through the screen. It's this constant dance between these 3 components.
So you've got these 3 core parts, but how do you arrange them? Well, there are a few ways, but one particular model, named after the brilliant mathematician John von Neumann, became the gold standard. It's the blueprint for almost every computer we use today.
The genius of the von Neumann architecture is its beautiful simplicity. The core idea is that the program, the list of instructions, is stored in the exact same memory as the data that the program uses. They live together, and they travel along the same information highway to get to the CPU.
But, and this is a really famous but, that elegant design has a major trade-off. It's called the von Neumann bottleneck. Since the instructions and the data have to share the same single-lane road to get to the CPU, you can get a traffic jam. The processor might be incredibly fast, but it ends up just sitting there, waiting for its next delivery to arrive.
Okay, so we've got the parts, we've got the blueprint, but how does a static collection of circuits actually do anything? The answer is a constant, rhythmic cycle that acts like the computer's heartbeat. This process is known as the instruction cycle, and it all boils down to 3 simple-sounding steps that repeat over and over and over again, billions of times every second. Fetch, decode, and execute. This is what brings software to life.
Let's walk through it. First, the CPU fetches an instruction from memory. Think of it like grabbing the next item on a to-do list. Then, it decodes it to figure out what it's being asked to do. Next, it executes the command. Adding 2 numbers, moving data, whatever it is. And finally, it stores the result back in memory. And then, the whole cycle starts again. Fetch, decode, execute, store. Over and over.
This flowchart gives you a sense of what that loop looks like. It might seem complicated, but remember the core idea is simple. It's a non-stop cycle. It grabs an instruction, figures it out, does the work, and then immediately moves on to the next one. This is the engine that powers literally everything your computer does.
Now, things get even more interesting. Even within that basic model, there are totally different philosophies about what the CPU's instructions should look like. This leads us to a major fork in the road, a big debate in computer design. RISC versus CISC.
All right, first up is RISC, which stands for Reduced Instruction Set Computer. The whole philosophy here is less is more. RISC processors have a small, limited vocabulary of very simple, highly optimized instructions. Each one does just one tiny thing, but it does it incredibly fast, usually in a single tick of the processor's internal clock.
And on the other side of the ring, you've got CISC, or Complex Instruction Set Computer. CISC's philosophy is the opposite. It wants to do more with each instruction. So it has a huge vocabulary of powerful, complex commands. A single CISC instruction might do the work of 3 or 4 RISC instructions all at once, like grabbing 2 numbers from memory, adding them, and storing the result all in one go.
And this table really lays out the differences. RISC is simple, lean, and mean, which makes it super power efficient. That's why ARM chips, which are RISC-based, are in almost every smartphone. CISC is more complex and powerful, letting you get more done with less code. And that's the world of the x86 chips from Intel and AMD that have powered PCs for decades. It's a classic trade-off between hardware simplicity and instruction power.
So, we've gone through all this technical stuff. The building blocks, the models, the design philosophies. Let's zoom back out and ask the most important question. Why does any of this matter? Why is this blueprint so incredibly important?
Well, it turns out it matters for pretty much everything. The architecture is what determines a computer's raw speed and performance. It affects power consumption, which is the whole game when it comes to battery life on our phones and laptops. It's the foundation that enables huge innovations like AI and cloud computing. A great architecture can even help make a system more secure from the very start. At the end of the day, these deep design choices define what our technology is capable of.
And that kind of leaves us with a really exciting question. Computer architecture is always evolving. As we demand more and more, smarter AI, more immersive virtual worlds, incredible efficiency, the blueprints we rely on today will have to change too. So you have to wonder, what will the computer blueprint of tomorrow look like?